Hi there, I'm Prof. Joe. I'm a professor for automation and measurement technology at the University of Kempten in the very south of Bavaria, and this is part of my lecture on measurement technology. Today we are going to talk about current measurements, especially using a real current meter to measure the current through any system we could imagine. Saying so, the first thing is we only have to look at one type of circuit. That is, we have a voltage source combined with an internal resistance. Why is this enough? Remembering last chapter, chapter 4, we know we can get any circuit into this form, combining all resistances within one internal resistance and combining all voltages or current sources within one voltage source. So this makes it easy for us. We just have to look at this type of circuit. Now, what do we want to do? Imagine this is any type of circuit and we want to measure the current in between those two connectors here. We can get to this form. So what we are going to do is, for sure, we are going to put our measurement device directly between those two connectors. Now, to get a glimpse into reality, what does that mean? Normally we have some complex circuit over here, and the very common case is that this voltage source is connected, for example, to something like a motor. And this motor has some resistance RB. And now we want to measure the current flowing through that motor, through that resistance. So we are going to connect that current meter in series with that resistor, with that motor we want to measure the current. That's the first important thing we have to deal with. We want to connect our meter in series with the resistor or the thing we want to know the current which is flowing through that thing. Meaning that right now when the current flows along here, it has to flow along our motor or resistance of any kind, and it has to flow through our current meter at the same time. So the same current I has to flow through both things, for example through our motor and through our current measurement device. So this is the first important thing. To make sure we are measuring the right current, the current we want to know, we have to put that current meter into series with the thing or the resistor we want to know the current which is flowing through it. So for our case, we can combine all of the resistances into that Ri, meaning that resistor Rb, which I marked beforehand over here, can be combined into that resistance Ri. So the thing we want to know is the current which is driven through the internal resistance by that voltage source, the short circuit current. Meaning we are directly connecting our current meter in between those two connectors. What we want to know is that short circuit current over here, flowing through Ri and now also flowing through our resistance of our current meter. So if we would have an ideal current meter, what we want to have is a resistance of Rm going to zero or being zero. So as we all know, that does not exist. There's always some resistance within the current meter. So what we wish is a current meter with a very low resistance. Having said so, we already know that we are making a lot of errors in here. So we don't know Ri exactly. We know our current meter will give us some errors we have to propagate through our whole system just by looking at its data sheet. But now we get some additional error we are introducing on ourselves and we know everything about. So we get our first glimpse of a systematic error. And that systematic error is that we are introducing that resistance into our system. What we want to know is that short circuit current without our resistance of our current meter. What we are measuring is our short circuit current with that resistance. So let's have a look at what that means. So dealing the same way as we talked about errors, our wish is to measure that short circuit current without the resistance, meaning the complete voltage falls over Ri, so we get as a current the voltage over the internal resistance. That is what we wish to know, because that is any circuit you can imagine, and we want to know at a certain place that current which is flowing, but we want to know it as if there would be no measurement device. So that is what we want to know. But what we are measuring is something different. We are measuring the current with our measurement device, which is the voltage which now falls along two resistances which are in series, Ri and Rm. So the current which can be driven is the voltage over Ri plus Rm. We see what we are measuring has to be a little bit too low, too small, because we add a resistance to the system, and that added resistance reduces the current. To get something more context for that, we can divide both sizes, our wish and our measurement, and get some more insight into the details of that behavior. And we get a behavior which is 1 over 1 plus the resistance of our measurement device over our internal resistance. So now let's look at that ratio in more detail. Drawing some graph with the ratio Rm over Ri over here, marked where the ratio is 1, and the resulting current ratio over here. So what we are expecting to get when we get below 1, that gets very small over here, and we get the thing we want to, we get that 1 over here, starting there, somewhere we get through that 1. At that place of being 1, we are at the place where the ratio of Im to Ik is 1/2, and over here we get into the bad areas. So looking at that, imagine we have a ratio of 1 to 100, meaning 10 to the minus 2. That will result in a ratio of Im to Ik which is nearly 1. So having such a ratio is fine. We can measure at that region without thinking too much about that systematic error. In that region over here, including those huge ratios, we should not measure. Now, what that tells us is, being in this area, the error is small. We are making due to the fact that we are adding some additional resistance to our system. When we are in this area, that error is large. But now, luckily, we just can calculate that error. We have everything we need to know about the stuff in order to calculate that error. So, let's just write that error down, because we already, as I said, know everything to write it down. So we have that error, we do some relative error, because we don't have quantities, we are calculating the relative error, which is now given by the error divided by our wish, which is, in fact, our short circuit current. Now, the absolute error over here is the measurement minus the short circuit current divided by the short circuit current, resulting in something like this, minus 1, which now we just have to insert the relationships we derived beforehand. So our measurement is our voltage over Ri plus Rb. Our short circuit current is our, no, the other way around, our voltage divided by only the internal resistance, so we can cross that out, minus 1, resulting in Ri over Ri plus Rb minus 1. And now, taking those two terms together will result in minus that is Rm, minus Rm over Ri plus Rm. So relative error. And now everything fits together, because the smaller our resistance of our measurement devices, the smaller this error in percent will get. The larger our internal resistance it is, the smaller it will get. So the smaller the ratio between the current measurement device resistance and the internal resistance, the resistance of our circuit system, the smaller this error will get. Anyways, that's a systematic error. We can correct it. So in reality, there's one problem, and that problem is, yeah, okay, sure, you're right. Writing it that way down, we can correct it, but we have a problem. We don't know about that internal resistance probably, because we don't know about that circuit. We just want to know the current. We don't want to know everything about that circuit over here. So Ri, we don't know about Ri, and at the same time, we don't know about Ik. So, because that's the thing we want to know. What we know, what we can measure, is the measured current. What we know, because it's on the data sheet, is the resistance of our current meter. So, what to do about that? Simple way, just do two measurements with different resistance Rm. What does that result in? We get two equations for two unknowns. The two unknowns are Ri and Ik. And now if we do two measurements with two different Rm1 and Rm2 resistances within the current meter, we get two equations with two different measurements. And we can calculate everything, the two unknowns in that equation system. So that means when we have current meter, we want to be able to have different internal resistances for the current meter when we want to do decent measurements. So, more expensive current meters will provide us with that. The older ones will simply include that behavior because of their different measurement ranges we can select, and every range will have a different internal resistance Rm. Not only for that reason, but for reasons of building the current meter. So when we have a current meter without those two different resistances, we can produce a current meter with a different internal resistance because we can simply add a known resistance to the system to get those two measurements. So we have everything to get to know of our wished current IK, which does not include the error which gets to life because of the internal resistance of our current meter. On the other hand, whenever you're doing measurements with the current meter in an, let's say, normal environment, meaning we have some larger resistances over here in the kilo ohm range, and our resistance of our current measurement device is in the range of ohms. So it's about a factor of 100 to 1000 smaller than all the other resistances. We know that there is an error, but for sure that error will be smaller than the error which is simply provided by the data sheet of our current measurement device. And for that reason, we, for a first glimpse, can ignore that systematic error. On the other hand, whenever we do an exact measurement, we do some quality management end of line in some industrial process, we have to calculate those errors. We have to diminish them. No, we have to remove them. We have to remove them because we can remove them. We know everything about them. So, next part will be about voltage measurement, which is quite similar. And if you like that stuff, feel free to subscribe. And in any other case, have fun doing some measurement technology.